Hello everyone, I'm Saurabh, a PhD student at Indian Institute of Technology, Bombay. In this presentation, I will be talking about solving practical allotment problems with Julia. Let us start with a quick introduction to the problem and motivation that got us excited. This started out as one of the projects to assist our department office staff in automating their tedious and time-consuming tasks. The problem statement here was to allot the best possible choice to each individual as per the preferences provided by them for available positions, while adhering to total available positions and satisfying certain quality constraints. I will break this down slowly as we get into the talk. This was a routine problem every semester. TAs needed to be allotted to courses as per their preferences for the course. Interview committees had to be allotted to candidates as per the match in their skill set during the admission intake every semester. There can potentially be other use cases for this problem, like allotting patients to hospitals as per the expertise available and the requirements of the patients, allotting college seats to the students as per their rank in a national entrance exam are two more examples. So the TA to course allotment problem was something which we were concerned with, and this was initially done manually, where the office staff had to sift through the TA preferences and course requirements data to arrive at a potential allotment after days of work. This was a tedious and time-taking job, and it could potentially lead to subpar allotments. The need from our work was to come up with an automated solution to this, which can run on a computer, requires no manual intervention, and consistently provides improved allotments, along with some quality metrics for how good their allotment is. Seeing this as a black box, we essentially want to come up with a solution which takes in TA preferences and course requirements and outputs an allotment in a way, a matching between them. For this, we model the problem as bipartite graph matching problem, where we have TA candidates on the one side and course on the other. An allotment is modeled as a matching between them, which can be denoted by an adjacency matrix of the edges connecting the courses in the TA nodes. The TA preferences and their capabilities are used to update these edge weights of the graph matching, that is allotment. Uh, the matrix is then updated using MCMC method while minimizing an objective function that is designed to capture the required quality constraints like student satisfaction, which refers to a TA getting his or her highest as high preference as possible. Uh, the course satisfaction, which refers to a course getting TAs who scored highest in the previous offering of the course, and the course feedback. Consistency of TA capabilities across courses, referring to a uniform distribution of TA capability across the courses. For fairness, consider let's formalize this a little bit. Consider two graphs S and C of the students and courses respectively. Our aim here is to find a good matching between them, which we can call an allotment. There can be many such perfect matching depending on the objective at hand, but we want to find a matching which is best in some sense. By best, we mean an allotment that satisfies our quality constraints for that particular problem. The quality of allotment, we call it as a utility of the allotment. We denote the preferences by edge weights or entries of the adjacency matrix, and here xn is used to denote the adjacency matrix. In the upcoming slide here, we have the proposed algorithm. It was a very simple algorithm. What we did was we populate the adjacency matrix with bucket filling allotment, where the TAs are allotted to first course in which comes up when sifting through the course requirements data in a serial order with no regards to their preferences. We swap the two rows of this allotment matrix xn and calculate the utility u of the newly allotted uh, newly arrived allotment and the older allotment. If the utility is higher, we update the xn to the new xn plus 1. If not, we only update it with a certain probability, which is a function of the difference between their utility. This simple process is repeated several times until we arrive at a point where the utility increase plateaus, and that is our solution. Here we show some comparison of the bucket filling allotment which we started off with, and what the result which we converged to after MCMC iterations. Here we can see that bucket filling allotment hardly any TA got their desired preference. The value 10 here denotes the unwanted courses, the courses which they never opted for, and that is expected because that is the bucket filling allotment is works like that. However, in MCMC based allotment, you can see that most of the students got their first preference, and almost all of them ended up getting one of the courses they opted for. Few of them did not get the courses which they opted for. That happens because of the design constraints which are there. Uh, Now, the other thing we can see here is we have a uniform distribution of TAs in the MCMC based allotment compared to the bucket filling allotment. You can see that the distribution is much better when in compared to the bucket filling allotment. So these are like the two metrics which can help us judge how good an allotment is. Uh, we can encode more such constraints while solving the optimization problem to arrive at a different solution depending on changing needs every semester. Now coming to the implementation part, we started off initially with an implementation in Python, which brought down the time required from days of work to a few CPU hours. Uh, there was no manual work involved. Now, the exciting part is when we ported this to Julia recently last semester, we got a speed up of 13x without doing any kind of code up optimization, which was super exciting. Due to the similar syntax of Julia and Python, there was minimal code rewriting effort when we ported the code, which was also very good. We could leverage multiple dispatch and uh, get significant gain in performance. Of course, there are more ready to use functions in Python as compared to Julia, but they can be rigid depending on one's requirements. They may be written in a way that they solve a subset or a superset of the problem which we are actually wanting to solve, and hence they can be inefficient because we still end up fitting the puzzle pieces together, uh, which can be inefficient. But this leads, but uh, uh, in Julia, since this ready-made functions were not there, this ended up being an advantage because this led me to find out alternate ways to implement the required functionality, which actually ended up being faster. Finally, the plotting. Finally, in Julia, plotting your first plot can be a little slow, but we seldom required it in this work. You can find the source code of this work on GitHub as a link on the slide. It is currently being packaged as a general purpose allotter to work for any allotment problem. Uh, yes, so that's all I had. Thank you very much for listening. Please feel free to reach out to me for any questions, and any feedback and suggestions are welcome on how I can improve upon this. Thank you very much.